Okay, today we're going to be talking about how to graph rational functions. And let's first review what a rational function is. A rational function is a fraction where the top is a polynomial and the bottom is also a polynomial. So the top is some function that has x's in it and the bottom also has x's in it. And when you divide those two, you get a rational function. So let's take a look at letter A. We want to use limits to describe the behavior of the function f at the values of x not in the domain. All right, so we know that actually the top doesn't have to have x's, could be a constant as well, as you see here. And we know that the parent function that we're going to be looking at how to transform is actually the function 1 over x. So 1 over x, if we can remember, looks like this. This is one of our parent functions. So we want to take this, we want to shift it right 7, and we want to reflect it over the x-axis, so we won't worry so much about the vertical stretch. So this new function is going to look like this here. So let's just say we have a vertical asymptote now at x equals 7. And instead of having the normal pattern that the parent function have, it's going to be reflected. So we're going to have this, and then we are going to have this. And we will learn how to graph them in later on in this video. But now we want to ask the question, as x is approaching 7, and this little plus sign says from the right, or from the positive numbers, what is the y value, because that's what f of x stands for, approaching, and this equal sign really could be written as an arrow. So let's just see what we have here. As x is approaching 7, so I'm on the x-axis, I'm approaching 7 from the right, and I'm going to trace the function. The function is heading down to negative infinity. So negative infinity. All right, now as x approaches 7 from the left, so I'm approaching 7 now, and I'm tracing the function. I'm getting closer to 7 on the x-axis, and I'm tracing the function. I'm looking at what the y value is doing. The y value is heading up to infinity. So there's that answer. All right, let's look at letter B. We can factor the bottom. We factor the bottom into x plus 4 and x minus 4. And we know from a previous lesson that the bottom gives us numbers that we are not allowed to plug into the function because we cannot divide by 0. So x cannot be 4 and x cannot be negative 4. So therefore, we will put vertical asymptotes on our graph at 4 and negative 4. So let's go ahead and do that. So here's one at 4, here's one at negative 4. And once again, we know that the normal pattern is like the first part is in this upper right-hand corner. We also know that the horizontal asymptote is going to be 0. We learned a few acronyms, Bobo, Bosco, Botno. This is going to be Bobo. You have a bigger power on the bottom. The horizontal asymptote is 0. So let's go ahead and put that on our graph. And as I started to say, normally the portion of the graph is going to be in the upper right-hand corner, but this is reflected over the x-axis. So therefore, it's going to be down here. And then there's going to be another portion here. And then there's going to be another portion there. And so now we have to analyze what is the function doing at both of these asymptotes from both sides. So we're going to say the limit as x approaches 4 from the right, f of x, or the y value, is approaching, I'm going to use an arrow, but it's really an equal sign. So let's approach 4 from the right. So I'm coming closer to 4 on the x-axis from the right, and I'm tracing the functions heading down to negative infinity. So I'm going to put a negative infinity here. And now I'm going to do the same thing on the other side as x approaches 4 from the left. What is the y value approaching? Well, if I'm approaching 4 from the left, I'm coming in this direction. I'm going to trace the function. The y value is heading up to infinity, so that's going to be infinity. Now I must do the same thing with the other asymptote. limit as x approaches negative 4 from the right. F of x is approaching, well, let's trace it. From the right, it is heading up to infinity. And then, of course, as x approaches negative 4 from the left, f of x, let's trace it. It's heading down to negative infinity. All right, so now you know how to analyze the function at the asymptotes from the right and from the left. Okay, example 2, we want to describe how the graph of the given function can be obtained by transforming the graph of the parent function 1 over x. All right, so when the function is written in this form, it's very difficult to figure out what transformations have occurred. So what we're going to do is we're going to use long division, or we could use synthetic division, but it's just as easy to do long division. So we're going to divide 3x minus 7 by x minus 2. And we're going to rewrite this function in a format that we can easily identify what transformations have occurred. So x goes into 3x 3 times. 3 times x is 3x. 3 times negative 2 is negative 6. And now we're going to subtract. 3x minus 3x is 0. Negative 7 minus a minus is going to make these both plus. That's going to make it a negative 1. So we can rewrite this now as this part 3 plus the remainder negative 1. We did this in 2.4 when we wrote a summary statement when we did long division. So that's basically what we have. So let's rewrite it in this way. Negative 1 over x minus 2 plus 3. Now we can identify the transformations. I see a right 2 units right there. So I'm going to write that down, right 2 units. And then I see a reflection over the x-axis. So reflection over x-axis. And then I see a shift up 3. So in doing long division, we're able to rewrite it in a format that we're able to identify the shifts and the transformation. Let's do the same thing here. Except I'm going to rewrite this as negative 3x plus 4 just because we're used to the x being the first term. So I'm going to put the x minus 5 here and then the negative 3x plus 4 here. Now x goes into negative 3x negative 3 times. Negative 3 times x is negative 3x. Negative 3 times negative 5 is a positive 15. We're going to subtract. That's going to be gone. I'm going to have 4 minus 15, which is basically going to give me a negative 11, so you got to be careful here. So we're going to end up with negative 3 plus negative 11, the remainder, over x minus 5. I like to rewrite it this way, negative 11 over x minus 5 minus 3. That way I can see all the transformations. So here we have a right 5. We have a reflection over the x, so over x-axis. I see a vertical stretch by 11 because we're multiplying the whole function by 11, so vertical stretch by 11. And then I see, as always, the last one is up and down, so down 3 units. Okay, I'm going to deviate from the notes a little bit and do some examples that I think are a little bit more representative of what you're going to see on quizzes and tests. So let's just start by trying to graph this rational function. In order to graph rational functions, you need 4 things. You need to be able to figure out the vertical asymptotes. You need to figure out the end behavior asymptote, which is either going to be a horizontal asymptote or, as we're getting ready to learn in a little bit, a slanted asymptote. We'll talk about that later. We need to know the x-intercepts, and this is all on your table and on the back of your notes. And we need to know the y-intercept. Okay, so let's just start with the vertical asymptotes. What we're going to do is we're going to factor the top and the bottom. So this is a difference of 2 squares, x plus 3, x minus 3. The bottom is going to factor into x minus 5 and x plus 2. Once again, the vertical asymptotes are going to be the numbers that make the bottom 0. So number 1, our vertical asymptotes are going to be x equals 5 and x equals negative 2. So let's go ahead and put those on our graph. All right, so we're going to put those in yellow. So x equals 5. So put that there, and then x equals -2. Okay, now horizontal asymptote is going to be obtained by using the Bobo-Bosco-Botno. So we have the same powers on the top and bottom, so we divide the coefficients 1 divided by 1. So we can see that the horizontal asymptote, which is the second thing that we need, that's going to be y equals 1. And make sure you're using y equals and x equals for these vertical and horizontal lines. Don't just say horizontal asymptote equals 1. That doesn't mean anything. You must have an equation for these dotted lines that you are drawing on your curve. All right, so now we need two other things. Let's get the y-intercept first. Now let's think about what a y-intercept is. I want to make sure you get the concept. The y-intercept is the point where a function crosses the y-axis. All right. Now on the y-axis, the x component is 0. For every point on the x-axis, on the y-axis, the x-coordinate is 0. So to get the y-intercept, all you do is simply plug in 0 into the function for all the x's. Well, when you plug in 0 into the original function, or this function, but it's the same function, the 0 here is going to go away, and you're going to be left with -9 on the top. And the 0 for these two x's go away, you're left with -10. -9 over -10 is a positive 9/10. So we can go ahead and put that point on our graph. We have to recognize, is it bigger than 1 or is it less than 1? Well, it's going to be slightly less than 1. All right, and then we have the x-intercept. Well, let's think about what an x-intercept is. An x-intercept is the point where it crosses the x-axis. So what is true when a function crosses the x-axis? Well, its y-coordinate is 0. So we're going to plug in 0 in here for y, which is f of x. So we're going to plug in 0, and we're going to get x squared minus 9 over x squared minus 3x minus 10. And we're going to multiply both sides by the denominator so that it will cancel out. And over here, we could multiply it as well, but we're just going to get 0, but I'll write it out anyway. Times 0. That's going to be 0. So really, we're left with x squared minus 9 equals 0. So we move that to the other side, and we get x equals plus or minus 3. So our x-intercepts are going to have coordinates 3, 0, and -3, 0. Once again, write them as ordered pairs. So I'm going to go here, 1, 2, 3, and I'm going to put a point. And then over here, I'm going to go here. And we know this is -2 as our vertical, so -3 is going to be right there. And we have all the things that we need now to graph our function. Well, we know that it has to go through this x-intercept, and it has to go through this y-intercept. Now, how many roots do we have here at 3? Well, look at the top. We have 1. That's an odd number. That's actually only one root, so it's going to follow the same. It's going to follow the same pattern as we learned in 2.3. It's going to go through the x-axis. So it's going to go through. It's not going to bounce. It's not going to slide. It's going to go through the y-intercept, and then it's going to come here, and it's going to go through the other x-intercept, and then it's going to come here, and it's going to approach that value here. So it's always going to go through the x-intercept or bounce over whatever, how many roots there are, and it's going to always approach the horizontal asymptote as x goes to infinity or -infinity. All right, let's try another example. All right, let's follow the same pattern and work on example 4. All right, we have x minus 1 over x squared minus x minus 6, and we want to sketch the graph of this. All right, what is the horizontal asymptote? Well, we have a bigger power on the bottom, x squared, as we do on the top, x to the first. So this is going to be our bigger on bottom, 0, Bobo. So y equals 0. So we're going to put that on our graph. There's our horizontal asymptote. All right, so we'll come back to the end behavior. Our domain range, will come back to those. Vertical asymptote, we're going to get by factoring the bottoms. So that's going to be x minus 1. And if we factor the bottom, it's going to be x minus 3, x plus 2. Set those equal to 0, and we get two vertical asymptotes, one at x equals 3 and one at x equals negative 2. So let's see if we can put those on our graph. Here's negative 2, and here is 3. All right, let's find the y-intercept. The order really doesn't matter. We said that the y-intercept is when the x-coordinate is 0. So we're going to plug in 0 for all of these x's, and we get negative 1 over negative 6, which is positive 1/6. So we're going to put that on our graph right around here. And then our x-intercepts are basically when you plug in 0 for the y-coordinate, and then when you multiply both sides by this denominator, it always goes away, and you're simply left with the numerator. So the little shortcut is to set the numerator equal to 0 to get the x-intercepts. When we do that, we get x equals 1. So an x-intercept of 1, 0. So I'm going to put that right here. And now we're able to sketch our function. So it's going to come up here. Oops, that doesn't look good. It's going to come up here. It's going to go through the x-intercept, through the y-intercept, and then it's going to show up on the other side and approach the horizontal asymptote. Then it's going to approach this horizontal asymptote right like that. Once again, we know it goes through here and doesn't bounce because there's only, if we put this in parentheses, only one root there. All right, now let's answer some of the other questions. End behavior. Well, end behavior is asking the question, the limit as x is approaching infinity. So what is the y value approaching? Well, as x gets bigger and bigger and bigger, trace the function, the y value is heading towards 0. And then you have to do the other one, the limit as x approaches negative infinity. F of x is also approaching 0. If you go this direction, it's going to be flattening out to 0. All right, the domain is going to be negative infinity to negative 2 in union with negative 2 to 3 in union with 3 to infinity. Range, the lowest value to the highest value. So that's going to be negative infinity to infinity. And then limits at vertical asymptote. Well, this is going to take a moment. The limit as x approaches, let's say, negative 2 from the right. So I'm approaching negative 2 from the right. I'm going to be tracing it. It's going up to infinity. And then I'll say the limit as x approaches negative 2 from the left. All right, so I'm going to trace the function. It's going down to negative infinity. Then we have to do the other asymptote. So the limit as x approaches 3 from the right. So as x approaches 3 from the right, not going right, but from the right, it's going to be up to infinity. And then the last one is the limit as x approaches 3 from the left. So I'm approaching 3 from the left, tracing the function, it's heading down to negative infinity. All right, now we are going to introduce a totally new concept to you, and it involves asymptotes that are not horizontal. And this is the new concept here. Notice that we've done a lot with Bobo and Bosco. Bobo meaning the power in the bottom is bigger, and Bosco, the powers are the same. You would divide the coefficients, but now we have not done much with Botno, when the power on the top is bigger than the power on the bottom. So let's circle that so that you can see. We have an x squared that's bigger than x to the first. Question is, how do we graph those types of things? Well, let's see if we can do it. We're going to factor the top, and that's going to be x plus 5 and x minus 1, and the bottom is x plus 3. So we're going to follow the same type of pattern here for a few of these things. We're going to first find the vertical asymptote. that's going to be setting the bottom equal to 0, so x equals -3. So we'll go ahead and put that on our graph. So x equals -3, no problem there. And then we're going to find the y-intercept. Y-intercept is when the x-coordinate is 0. So we're going to plug in 0 for all of these x's. And we get -5 over 3, so -5/3. No problem there. So we'll put the point 0, -5/3 on our graph. So we'll put that right there. And then we're going to find the x-intercepts. We said we get those by setting the numerator equal to 0. So that's going to be -5, 0, and 1, 0. All right, so let's go ahead and put those on our graph. 1, 0 is going to be right there. And -5, 0 is going to be right there. Now, the new concept is finding what's called the slant asymptote. Slant asymptote. It's not a horizontal asymptote. It's going to be a slant asymptote. You get that by a little bit of synthetic division. So we're going to divide x squared plus 4x minus 5 over x plus 3. So I'm going to put -3 in the box. And you have 1, 4, -5. Bring down the 1. -3 times 1 is -3. 4 plus -3 is 1. -3 plus 1 is -3. And it's going to be -8. Now for these problems, you don't need to use the remainder at all. But the coefficients that you have left here are going to give you your slant asymptote. So y equals x plus 1 is your slant asymptote. I'm going to draw that in green. So what we're going to do is we're going to put an asymptote that's not horizontal. We're going to start at the y-intercept of 1. When we say y-intercept, not the y-intercept of the original function, but the y-intercept of the asymptote. So that's going to be 1. And then it's going to have a slope of 1. So that means down 1 over 1. And it's make sure that you figure out where it crosses the x-axis so that you can draw a proper graph. So I'm going to draw a dotted line that represents our slanted asymptote. Now we're able to see pretty much what this graph is going to look like. It's going to look weird because it's something that you've never really done before, but it's going to come from here because it has to be close to the vertical asymptotes. So let me draw a couple of those things in there. So it's going to come from the close to the asymptote, through the y-intercept, through the x-intercept, and then it's going to get closer and closer to this other asymptote, the slant asymptote. And then on the other side, it's going to come down here as it's very close to the asymptote, go through the x-intercept, and then it's going to get closer to the green asymptote. And that's what the graph looks like. It's a very weird looking graph, but that's what it looks like. Let's do another example as well. All right, now that we've seen this done a few times, we should be able to be pretty good at it. We're going to find our 4 special elements of this graph. So we're going to factor the top into x minus 2, x plus 1. And after you do a few of these, you'll be really good at it. So we're going to find the vertical asymptote. That's going to be from setting the bottom equal to 0, so x equals 5. So let's go ahead and put that on our graph. So 1, 2, 3, 4, 5. Let's go ahead and put our vertical asymptote on our graph. And then we're going to find our y-intercept. And that's when you plug in 0 for all the x's, and you get -2 over -5, so that's a positive 2/5. Let's go ahead and put that on our graph. So if this is 1, 2/5 is going to be slightly below that. And then we're going to set our numerator equal to 0 to get our x-intercepts. So that's going to give us 2, 0 and -1, 0. This is our x-intercepts. So let's go ahead and put those on our graph. So 2, 0 is going to be here, and -1, 0 is going to be right there. All right, and now the last thing we have to do is find this new thing called the slanted asymptote. We get that by doing a little synthetic division. So x minus 5, so we're going to put 5 in the box. And our coefficients are 1, -1, -2. Bring down to 1. 5 times 1 is 5. -1 and 5 is 4. And we really don't even need to do this other part because we do not use the remainder in this situation. So our slanted asymptote is simply going to be y equals x plus 4. So let's see if we can graph that. So it's going to have a y-intercept of 4. So let's go ahead and put that on our graph. So 1, 2, 3, 4. And I'm going to put this in blue. So that's going to be our y-intercept. Our slope is 1. So I'll go down 4 and over 4, which is still a slope of 1. And so we will graph our slanted asymptote. And let me go ahead and draw a little bit more of this here because we're going to need that. And we are ready to graph our function. Well, we know that it always has to get close to the asymptote. It's going to go through the x-intercept, through the y-intercept, through the other x-intercept, and get close to the asymptote. And then don't forget on the other side, there's this other piece here that's going to be close to both of these asymptotes. And that, my friends, is how you graph the slanted asymptote.